Hi, I'm Claire, and I'm going to be presenting today on Archimedes, his life, and the measurement of the circle. So just some background on Archimedes. He lived around 287 to 212 BC, and he was a Greek mathematician, physicist, philosopher, engineer, and astronomer. So because he lived so long ago, very little is actually known about his life. All that we know is any documents and things that have been recovered, but we know him mostly by his accomplishments. We don't really know much about his personal life. He is considered to be one of the greatest mathematicians of ancient times, and some even will consider him to be the greatest mathematician of all time just because of how profound his discoveries were and the great effect that they've had on mathematics. A lot of his discoveries we still use in modern days, which is pretty incredible. And so he was killed by a Roman soldier during the siege of Syracuse at the age of 75. There's actually a story that goes with this that's pretty interesting, and we don't know necessarily if it's true, but the story goes that he was working on a math problem when they found him, and he was ordered to go to the soldier. The soldier ordered him to come with him, but he refused to leave because he was so focused on his math problem that he was trying to figure out. And the soldier got angry and killed him, despite being specifically ordered not to kill him, since the leader of the invasion recognized that he was such an asset to science and mathematics that he was ordered not to be killed. However, the Roman soldier was enraged, and so he killed him anyways. So Archimedes requested that two statues of a cylinder and a sphere be put at his tomb to commemorate his favorite proof. And that proof was that if you have a cylinder and a sphere of equal height or diameter, then the volume and the surface area of the sphere and the cylinder, the volume and surface area of the sphere are both 2/3 that of the cylinder. And so that was Archimedes' favorite proof. And to commemorate that, he wanted the statues of representing those two shapes by his tomb. Today, we currently don't know where he was buried and have never discovered his tomb, but we know that just from what was recorded during the time. So some of his contributions to mathematics, this isn't everything that he did, but these are just a few of his key discoveries. He came up with an accurate approximation of pi. He came up with the area of the circle. He found formulas for surface area and volume of a sphere. Also, he found formulas for the area of an ellipse, and the area under a parabola. So that's just a handful of his key discoveries in mathematics. So I'm not going to be talking about all that today. What I'm going to be talking about specifically is a document that is called Measurement of a Circle. And this is a series of 3 propositions made by Archimedes. Now, Archimedes didn't put together Measurement of a Circle. The document itself, it was put together by someone else who came across his discoveries and organized them. So Measurement of a Circle wasn't made by Archimedes, but the propositions that it contains are propositions directly discovered and written by Archimedes. So Proposition 1 states that the area of any given circle is equal to that of a right triangle with one leg equal to the radius and the other leg equal to the circumference of the circle. And so you can see in this diagram here, it kind of shows what that would look like, where you have your triangle with the radius and the circumference as the legs. And it's pretty easy to see how you would get those two areas to be equal, because if you, knowing that the circumference is equal to 2 pi r, if we replace the c in the triangle down here with 2 pi r, and then apply the area of a triangle formula to that, we would get 1/2 of 2 pi r squared, which simplifies to pi r squared, which we know as the area of the circle. So it's pretty easy for us to tell that those two areas are equal. However, at the time of Archimedes, we didn't even have the measurement for pi yet, and we'll see later that Archimedes comes up with the approximation for that. But before that, we had no way of knowing what the area of a circle is. So the way that Archimedes solves for the area of the circle is he uses the method of exhaustion to prove that this statement is true. And so basically, the method of exhaustion, how that works, is that you take a series of polygons and you fill a shape that we're trying to find the area of, but we have no way of solving for it. So take the area of the circle, for instance. He didn't have a formula for the area of the circle, so he inscribed a series of polygons into the circle and then added the sum of all the areas of those polygons and was able to get a very close approximation for the area of the circle. And so that's how he goes about proving this. The next proposition that Archimedes has is proposition 2, which states the area of a circle is to the square on its diameter as 11 is to 14. And so as it turns out, that this proposition actually relies on the results of the third proposition to be able to prove that this is true. And you'll see later that the proposition 3 deals with approximating pi, but without the approximation for pi, there's no way of solving for the area of this circle. And so there is no way of showing that proposition holds true without proposition 3. So what this means is that Archimedes did not actually place the propositions in the order himself. This was done by someone who created the measurement of a circle document after Archimedes. When they were organizing it, they put it together in that order. But Archimedes himself would not have put it together in that order because that wasn't actually the order that the propositions went in when he discovered them. So proposition 3, like I said earlier, deals with approximating pi. And so proposition 3 states that the radius of a circumference of any circle to its diameter is greater than 3 and 10 out of 71, but is less than 3 and 1/7. So in other words, if we simplify those two mixed numbers into decimals, that gives us 3.140845 and 3.142857. So what he's basically doing here is giving the approximation for pi, saying that it's between those two numbers. And we know that because the ratio of the circumference to a diameter is pi. So essentially that's what he's finding here. And during Archimedes' time, they didn't have the concept of pi yet. He was the first to kind of discover this idea or come up with the concept of pi. So he didn't really have a name for it yet. You know, the term pi wasn't really coined till later for this number. But essentially, that's what he's finding. And so how he goes about acquiring this approximation, because again, they didn't have the formulas that we have today, and that's why he had to approximate it, is that he inscribes and circumscribes a circle with two similar 97-sided regular polygons. And so what that's going to look like is I have this picture down here that's showing a circle being inscribed and circumscribed by a hexagon. And you'll notice that in the first one, the hexagon diameter is going to be less than the circle because it's inside the circle, but it's going to be greater than the circle on the second picture because it is bigger than the circle. And so what he does is he uses a 96-sided regular polygon because the more sides that you get, the closer to a circle it's going to be. So the thought process here was that if he uses a shape that is still technically a polygon, so it still has straight sides, and he can still measure the lengths of the sides, he will be able to find the circumference, or close to the circumference of what that circle would be. And so he does it with an inscribed one, knowing that it's going to be slightly smaller than the actual circumference, and then the circumscribed one where it's going to be slightly greater than the circumference. And that's how, and then he compares the ratio of both of those circumferences to the diameter, and that's how he ends up with the numbers shown above. All right, so that's all I have for this presentation. Here are my sources, and thank you for watching.